Hello, this is the presentation for our paper, Weighted Distinct Sampling, Cardinality Estimation for SPJ Queries. I am Yuan Qiu from HKUST. SPJ stands for Select, Project, and Join. They are the three most basic database operators in database queries. An SPJ queries is represented like this in relational algebra, or as a select from where clause in SQL. For example, in a TBCH-like query, if we would like to find all the customers who placed an order after a certain date, we may issue a query like select the customer key from the orders table where the order date is larger than the given date. If we further require that this order must contain an item whose price is more than 100, then we'll have to join with the line item table and add another selection predicate. Many SQL queries are built upon basic SPJ blocks. Therefore, accurate cardinality estimation for these queries is an important problem. In the literature, each of these operators have been extensively studied, but only separately. For selection, the problem is usually known as selectivity estimation. Solutions include sampling and making assumptions like the data is uniformly distributed or the selection conditions are independent. There are better solutions when the predicates are limited to a certain form, for example, range queries. For projection, the definition is a bit different in SQL versus in relational algebra. In SQL, a select operator does not automatically remove duplicates. And in this case, the cardinality of the dataset is not affected. However, in relational algebra, or if we have a distinct operator in SQL, then duplicates must be removed. And the problem is usually called distinct counting in the literature. Note that this also corresponds to the size of a group by query in SQL. And there are also different techniques solving this problem. For example, those based on summaries, including FM sketch, hyperlog, and K minimum values summary, and those based on sampling, including uniform sampling and distinct sampling. For joins, the join size estimation problem is also well studied. We have sketch-based techniques like AMS sketch and const sketch. And also we have sampling-based techniques like ripple join, Warner join, and two-level sampling, etc. But in practice, these operators rarely appear on their own. So we are interested in cardinality estimation for a combination of these operators. For a selection plus a join, this does not seem a big challenge as we can always rewrite the selection condition into the join condition as a zeta join. But what about the combination of a selection and a projection, or when we have all these three operators combined together? This is the focus of our paper. Let us first review an algorithm called distinct sampling that solves the problem for SPJ queries. We start with the basic case where there are projection only, and our target is to do the distinct count estimation in a multiset. And to do this, we sample each distinct value with some probability P to form a sample set AX. And how do we do it? We first hash each value to a hopefully different hash value, and then we perform sampling based on their hash values. Note that the duplicates will be removed during this hashing procedure. And it is known that the sample size scaled out by the inverse of P will be a good estimator for the distinct count D. It is unbiased, and its variance is roughly D over P. And in this concrete example, let's say we sample each distinct value with probability 1/2, and we obtain a sample that contains values 1, 3, 4, and 6. And our estimator will be the sample size, which is 4 in this case, divided by the sampling probability, which is 1/2. And we get 8 as our estimator, where the actual distinct count in this example will be 6. And now let's move to the selection and projection case and see how this algorithm can be used to solve the problem for SPJ queries. So what we want to estimate is the number of distinct values in the relation after a filter condition phi is applied to the relation. So to support arbitrary selection conditions, a natural idea is to augment each distinct sample with some tuples from the original table. And under the space constraint, we can augment each sample with tau of its tuples, which are uniformly taken from all the tuples associated with the value. And this indeed creates a sample relation. So we can simply use the distinct count in the sample relation after the filter condition is applied and scale it up by 1/p as well to form an estimator. So look back into our example. Again, say p is equal to 1/2, and we sample the values 1, 3, 4, and 6. Now say we want to augment each tuple with each value with 2 tuples from the original table. So our tau is equal to 2. And for 1, 3, and 4, they each have at most 2 tuples. So we can store all their tuples to be associated with the value. But for value 6, it has 4 tuples, and we are not allowed to store all of them. So we're going to just uniformly take 2 out of its tuples. So let's say we take the tuples where b is equal to 80 and b is equal to 60. And now we received a filter condition that passes a tuple whenever b is less than 10 times 8. I have marked here that those tuples that pass this filter condition. So in the original table, each of the values in 2, 3, 4, 5, and 6 observed at least one passing tuple. Therefore, the distinct count in the original table after the filter condition is applied will be 5. And now looking into our samples. So this is our sample relation. And in our sample relation, only 3 and 4 observed a passing tuple. So we are going to use this distinct count in the sample relation after the filter, which is 2, divided by the sampling probability, which is 1/2 in our example. And we get an estimator of 4 when the actual value is 5. So our question is this estimator good? Well, if we could augment each value with all its tuples, then the estimator would degenerate to the projection only case, which would then be unbiased with variance d/p. But since we are only allowed to store tau of the tuples, so it is possible that some passing tuples are not sampled, are not stored by our sample, even if there are some. So looking back into our example, so actually for value 6, it has 2 passing tuples. It has 2 tuples that pass the filter 5, but we are unfortunate that our sample did not catch that. And so we could not, we don't have a passing tuple sampled for value 6. And this indeed creates a downward bias. So because our expected sample size is d times p times tau, so we cannot have a large p and a large tau at the same time. And the problem is how to balance. In the original paper, the authors just used a heuristic, but we will show next that there are some bad instances where you cannot set the parameters to be good. So this is our hard case. We have square root of d heavy hitters. Each heavy hitter has 3 square root of d tuples, and the remaining values are light, and each light value has only 1 tuple. So in total, we have d distinct values and roughly 4 d tuples, only subtracting a lower order term. And we're going to use 2d sample budget, which is actually storing half of the tuples. For the uniform distinct sampling algorithm that we just described, its mean squared error is at least d. And the intuition is that if we set tau to be large, then p can only be small. Actually, p can only be a constant. And remember that the variance is calculated by d/p. So when p is a constant, the variance would be d. On the other hand, if we set tau to be small, say tau is less than or equal to 2 square root of d, then for each of the heavy values, we are only storing a constant fraction of its tuples. That means in the worst case, the bias would be constant for each of the heavy hitter. And since we have square root of d heavy hitters, the total bias would be square root of d. And recall that the mean square error is calculated as the square of the bias plus the variance. So in either case, the mean square error would be d. So can we do better in this case? Well, the answer is yes. For this instance, there is a simple strategy that is better. We are going to deterministically store all the light values, which were going to consume d of our sample budget. And then for each heavy value, we're going to sample it with probability 1/3. But whenever a heavy value gets sampled, all its tuples will be stored. We can check that this consumes another D from the sample budget in expectation. And then we can show that the mean square error of this algorithm would be square root of D. So an intuition is that because we are storing all the tuples associated with the value whenever a value gets sampled, so there won't be a bias. And because the light hitters are handled deterministically, so the variance only comes from the heavy hitters. And since the variance is square root of D or P, and our P is the constant, so the variance here is only square root of D. And that's just the mean square error. So this suggests that our sampling probability shouldn't be uniform. Instead, it should depend on the frequency of each value. But why? Why should we use weighted distinct sampling? Well, this is because of two reasons. First, in the distinct counting estimation problem, the heavy hitters are not more important, like they are in many other applications, for example, frequency estimation. This is because any distinct value can only contribute 1 to the final distinct count after the filter, no matter what their frequency is. However, the heavy hitters are indeed harder to estimate in the worst case. For light hitters, we can store all its tuples to remove the bias, while for heavy hitters, we must spend more tuples on them to catch the passing tuple. This brings us the weighted distinct sampling algorithm. It works just like the uniform distinct sampling algorithm, except for that our sampling probability Pi and the number of tuples stored for each value I are both vectors specific to each distinct value. We're going to correspondingly modify our estimator to be the sum of 1 over Pi for those value i's that both get sampled and observe a passing tuple in its samples. When the vectors are uniform, our algorithm degenerates into the uniform distinct sampling case. So our next question to ask is, what are the best parameters? Well, it turns out this is not an easy problem, but we managed to give a near optimal solution. So in general, our near optimal solution looks like this. We'll have our sampling probability Pi inversely proportional to the square root of the frequency of any value. And whenever a value gets sampled, we should keep all its tuples. And there are two exceptions. First, when the frequency is too small, the sampling probability, of course, should be upper bounded by 1, which means we deterministically store the value and its tuples. And when the frequency is too large, we are not going to sample the value at all. So here are some intuitions. Remember that the heavy hitters are harder to estimate. So indeed, our sampling probability Pi is decreasing with respect to the frequencies. And because bias is more important than the variance, so whenever we sample a value, we should keep all the tuples associated with it, instead of keeping less tuples and allow more values to get sampled. And for any value I, its cost to the sample budget is actually proportional to square root of Ni. And for large Ni's, the cost would outweigh the benefits. So we are going to decide not to sample them at all. And here is a concrete example. So this is our histogram, and our sample size is 20. The near optimal solution says that for the first 6 values, we are going to deterministically put them into our sample, which consumes 9 of our sample budget. For the next 3 values, their sampling probabilities are this, and they can be verified to be inversely proportional to their frequencies. And once they are sampled, we are going to keep all their tuples. And you can calculate that the expected consumption to the sample budget would be 11. And the last value, 10, has frequency 20, which is too large. And the algorithm will decide not to sample the value at all, which brings 0 cost to the sample budget. Say in one execution, we obtain the following sample, which is actually marked in blue here. So instead of, in addition to 1 to 6, we also sampled 7 and 9. And now we get a filter that passes 1 tuple for each of the distinct values. That means the distinct count after the filter condition is applied is still 10. And our estimator will be calculated as this. So recall that we actually keep all the tuples associated with the value when the value gets sampled. So the passing tuple must be identified by our algorithm. So the estimator for the first 6 values will be 6. And for 7 and 9, their individual estimators will be the inverse of their sampling probability, which is the inverse of 0.93 and the inverse of 0.57 respectively. And so the total estimator would be 8.82 when the actual distinct count is 10. So this is how our algorithm works for SP queries. And now let's move to SPJ queries. There are no existing solutions except for the trivial upper bounds, which are derived from the join sizes. Of course, if we calculate the join result, then we run our weighted distinct sampling algorithm on the join result, we can solve the problem. But usually the join itself is the most time-consuming part. So we plan to do much faster. This is achieved by doing random walks in the join graph, which is using similar ideas to the Warner join algorithm. And we view the join as a graph, where the vertices are the tuples in all relations. We add another D vertices that represents the distinct values in our query column. So correspondingly, there are 2 types of edges. First, between a value and the tuple that contains the value. And second, between 2 joining tuples. And this is an example for line join between R and S and T. And the query column A is contained in relation R. And our algorithm starts by running our weighted distinct sampling algorithm, our single table weighted distinct sampling algorithm on table R that contains the query column. And we're going to scale the parameter tau up by a constant because we expand that we expect that the joins will expand the tuples into join results, into many join results. And for each sampled value in our first step, what we actually do is doing a breadth-first search in the join graph while searching for the join results. And while doing this, we are being careful not to break the sample budgets. And since we cannot traverse all the join results, there will be a bias. So in addition to our weighted distinct sampling estimator in our single table version, we also do some bias correction, which is too detailed to be described here. And here are some of our experimental results. For SP queries, our weighted distinct sampling algorithm generally outperforms uniform distinct sampling, especially when the filter is hard or when the data is skewed. For SPJ queries, the difference is less significant, but our random walk algorithm saves the sample construction time by orders of magnitude. And so here is our conclusion. We have introduced the weighted distinct sampling algorithm to solve the cardinality estimation problem for SP queries and SPJ queries. This is implemented in AnalyticDB, which is a product of Alibaba Cloud. And for future directions, here are some interesting problems to investigate in. Firstly, our current algorithm actually requires solving the sampling parameters before we actually collect the samples. So it is interesting to see whether we can do it on the fly, and that means dynamically maintain a sample. And secondly, it is known that for the selection-only case, if the predicate is limited to a certain form, for example, range queries, we can do much better. So for our problem, we actually solve the problem for general SP queries, which means the selection predicate can be arbitrary. So it is possible that when limited to certain forms, for example, range queries, we can also do much better by using some sketching-based techniques. Okay, so that's all for my presentation. Thank you for listening.